All right, we're going to be going on 14.4. This is the chain. Well, my C didn't turn out very well. The chain rule. All right, so here we're doing chain rule with partial derivatives and multiple variables here. So, all right, let's take a look. So theorem 5, the chain rule for functions of two independent variables, if w equals f of x and y, has continuous partial derivatives, fx and fy, and if x equals x of t, y equals y of t are differentiable functions of t, then the composite w equals a function of x of t, y of t is a differentiable function of t. In other words, we can go through and replace x and y with t and make w totally into a function of t, and therefore we should be able to take the derivative of w with respect to t. And we can do this by simple matters of the chain rule. And so you can see the two versions of it there. You have this way, which is not my favorite. I am more of a fan of thinking of it this way right here, where you can see and you can still kind of think like the previous chain rules where the dx's would cancel and you have df dt there, looking at your functions like that. So partial derivative of your function, f of whatever f of x, y is with respect to x times then the derivative dx dt. Notice we have partial derivatives here because x is a function, or f is a function of x and y. Here we have just regular old derivative because x is only a function of t in that case. So we don't do the partial derivatives there. All right, and the same thing here, partial and regular right there. All right, so continuing on, a little what's called a tree diagram to help you try and remember this. So you're starting off with w and you're trying to get down to a derivative of dw dt, and so you're just going to take both paths. You go along this path to do dw dx because f is a function of x, and then do dx dt and bring those together and gives you this part, and then this one tells you you do the other one with respect to w to get to there and then to there, and again that gets you that part. Add the two branches together and you get the total derivative for it with respect to t. So you have to do the partials and then add them up. Okay, here use the chain rule to find the derivative of w equals x times y with respect to t along this. So what we're going to say is we want dw dt, right? So that's what we're trying to get here is this dw dt, and so we have to do partial w partial x times dx dt, so that's what we got to do, and then do that with y. dw dx dt dx dt, I'll get it, dx dt plus partial w partial y dy dt. So if we calculate each one of these, we can combine them all back together. So partial w partial x is just going to be from right here, and that's just going to equal y, and then partial, or not partial, dx dt we'll get from looking at x as a function of time right there. Derivative cosine is negative sine of t, so we have that one. Now we need partial w partial y here, and so that's going to come again from this one up here, w equals xy, and so we take the derivative with respect to y, and that's just going to equal x. And then we have to look over here and do dy dt, which we'll get from y equals sine of t, derivative of sine is cosine t. So if we start putting those all together, we get dw dt equals y times negative sine t, all right, that's this and this for right there, plus partial w partial y, which is just x, times dy dt, which is cosine t, like that. And so we have this right here, and then what we can do is actually substitute in. We know that x equals cosine t and y equals sine t, so we can substitute those in. So substituting for y, we get negative sine squared t, and then substituting cosine for x, we get plus cosine squared t. All right, and that is our result there. The only thing left you could do is actually do this last part, is they wanted at t equals pi over 2, and so you could plug in this pi over 2. So we could do dw dt evaluated at pi over 2. And so we get negative sine squared of pi over 2 plus cosine squared of pi over 2. And so pi over 2 is where cosine is 0, so that's 0, and sine is 1. So this becomes just negative 1 right there as our answer, okay? Because it's the negative of sine squared, not negative sine times negative sine. Okay, so there's your answer for that one. Let's move on here. Chain rule for when we have 3 functions. It's pretty much just an extension. If you have x, y, and z, you do the same sort of thing. You just add this extra term on here at the end. All right, just add on doing it for z as well. And then you've got that. Here is a tree for that. You just add on an extra path, an extra branch, I guess, for this. And you can see you go from the dependent variable through what are called these intermediate variables, where they are each functions of t. So they're the intermediates, and then your actual independent variable there, t. Okay, so you just go through them like that and do all 3 paths, add them up. So after this, here's an example done for you. Find dw dt if w equals xy plus z, and x equals cosine t, y equals sine of t, and z equals t. So in this example, the values of wt are changing along the path of a helix, right? We've seen this helix before. What is the derivatives value at t equals 0? So you go in and do your derivative dw dt by using the partial derivatives with respect to x, y, and z, right? X with respect to x, y, and z, and then do the actual chain rule and add on the dx, dt, dy, dt, dz, dt parts, and go through and do it. And so dw, or partial w partial x, is just going to be a y, because the derivative of x is 1, and we treat y as a constant. And the derivative of z, we're treating it as a constant there, so it just goes to 0. And you just go through and do the rest of the derivatives. Dx dt would just be negative sine right from there, so that's that right there. Do the other 2 terms, start combining and reducing, and so then you get your ultimate result that here is dw dt, and then you can go ahead and plug in t equals 0 and get a value of 2. All right, so not really anything, I guess, more to understand there. It's just you do that extra step of also including it for the 3rd variable. All right, here's the chain rule. If we have 2 independent variables, essentially what you're going to do is you can do it, if you have a function of x, y, and z, and then those functions themselves, x, y, and z, are each functions of 2 other variables. That means we can take 2 different partial derivatives, ultimately, of our function w, one with respect to r and one with respect to s. And because of that, we basically just split them. And when you're doing the one dw, or partial w partial r, you're just going to treat s as a constant while you do that one, because you're doing partial derivatives here. Notice now the big difference here is this stayed a partial derivative, but this has become a partial derivative itself, because now x is a function of r and s, and we're taking its derivative, we're taking a partial derivative there, not an implicit derivative of it. Okay, and so we're treating r and s there, we treat s as a constant here. And then the same thing down here, our second little pieces there became partial derivatives now because of that secondary dependence on, or that dependence on now 2 variables there. So we're switching over to the partial derivatives there. Okay, but otherwise pretty much the same. You can just do it for each one individually. So let's take a look here, some tree diagrams. First, the one that you can see here, of course, the dependent, independent, and the intermediate variables there in the middle. Here you can see where we're tree diagramming it if we're going to do it with respect to r. And so notice these first parts are the same, right? But it's the secondary steps here where we then do partial derivatives with respect to r there, and partial derivatives with respect to x there. And so really the only parts that are changing are these little second parts of the chain rule there, right? Where we're changing those second ones from drs to ds's, and then that gets us which one we're taking a partial derivative with respect to. All right, so take a look here. Here's an example where they go through and find partial w partial r and partial w partial s in terms of r and s. So again, you start off, they do the first one, they just follow the rule as it is and just pretend s is a constant. And so you end up with this result down here. And then in the other one, you go through and do it, but with respect to s, and pretend that r, and treat r as a constant there. And so that's what you get there. So you get two different results there, depending on which one you're looking at, which derivative you're looking at, partial derivative with respect to r or with s. Here, you can see now we can do the same sort of thing where we have a function that is a function of x and y, but we just have x and y are also still functions of r and s. So function of xy, and then x is a function of rs, and y is a function of r and s. So this is kind of like the previous version we did with all three. We just don't have to have that plus z terms over here, right? We don't have the plus z terms out there. So just kind of a simplified version there, but it'll still work if you go back down to something like that. Okay, and there is a nice tree diagram for this one again, and you can see that it works again. You just don't have that third branch to go through. Next, take a look at this one, tree diagram for differentiating f as a composite function of r and s. All right, so w is a function of x, and x then can be taken as a derivative. All right, just x is so x itself is a function of r and s, but w is just a function of x. And so you can split it out like that. So dw, or partial w partial r, you're just going to have just this one term. So we're simplifying it further down. So basically x is a function of r and s, like this. And then the second derivative for partial w partial s, and just doing it for x. But notice now this becomes the regular old derivative, whereas the second one is the partial now, because x is a function of r and s in this example. All right, here we have a tree diagram differentiating w equal to a function of x and y with respect to x. Okay, and if we actually go through and set dw dx equal to 0, then we can actually get a simple computational formula for implicit derivatives. All right, so if we take that part out of there, we have an implicit derivative. So if we do that, we get this right here. Essentially what we get is that suppose that f of xy is differentiable, and the equation f of xy equals 0 defines y as a differentiable function. So if we set our z and we just project this into the xy plane, essentially, we get a function purely of x, y, and we can say y then becomes a differentiable function of x, so like our regular old ones. Then at any point where the partial derivative of f does not equal 0, we can say that our implicit derivative is simply the negative of the ratio of our partial derivatives there. So we can do this, and it actually can work out to be a lot simpler for doing this. And then of course we can extend this out to doing it for z as well with respect to x, and z with respect to y rather than just y. All right, so we can go out to where we have the three variables here and extend that out a little further and do dz, or partial z partial x, and partial z partial y right there by doing that. All right, so take a look here. I think this is our last page. Yep. So here we have used theorem 8 to find dy dx if y squared minus x squared minus sine xy equals 0. And so basically we're going to do this with what we just came up with on the other page. We're going to say dy dx equals the negative of the ratio of the two partial derivatives, one with respect to x, one with respect to y. So here is the partial derivative with respect to x, here's the partial derivative with respect to y, there is that negative sign. Put them together, and there you go, you've got that. If you want to, and I actually recommend it, go back and try doing this the way we did it before, where you have to do, you know, 2y dy dx minus 2x dx dx minus, and then start chain ruling and go through and do that whole thing, and see if you can come up with what dy dx is that way, and you should get that same answer. But this way is significantly faster and simpler to do. All right, so that's it for this section. Thanks for listening, and we'll see you on the next one.